Hi everyone, great to see you this afternoon for today's Real Data Science Meetup, where we'll be talking about large language models and how to optimize them. Real sort of topic du jour at the moment. So today with me I have Ziad Francis, data scientist here at PA Consulting, who's going to lead the bulk of the discussion around a lot of the work you've been doing in an area of interest at the moment in data science. Before we get to that though, we're going to lead off as usual with a bit of a chat to get to better know Ziad, your career journey, and a bit of context around the topic and why we're actually talking about large language models at the moment. And lastly, in case this is your first time joining us here, I'll give a quick intro on what the Real Data Science Meetups actually are. So there's a series of global live streams and in-person events running every 6 weeks out of London, Utrecht, Denver, and Copenhagen, where data scientists from our team here at PA Consulting go deep and really present a blend of theory, code walkthrough, and historical context around particular areas of interest in AI and machine learning. The hope here is that these sessions are fun, a chance to learn something and actually engage with sort of technical code as well as just the surface level, what can it do for you. So if you want to follow the series, which I'd heartily recommend, and see where and when the upcoming events are going to be, or provide any feedback or suggestions about what you'd like to see us tackle next, make sure to follow our Meetup network or subscribe to our YouTube channel, Real Data Science. So, with that preamble out the way, time for the fun stuff. Thank you for joining us today, Ziad.
Thank you, Max.
As usual, I'm gonna grill you for a little bit, but I think it's nice because it's sort of, we have a real range of people who get to data science and join our team at PA, and in the community at large, I think it's a real breadth of experience that leads people to this career path, and so I really enjoy having these chats. The first question, which is the easy one to sort of lead off, is I guess what brought you here to sort of the career journey and be right now at a place like PA as a data scientist and machine learning expert?
I think I come from physics. My background is radiation physics, and I started using numerical modeling and numerical tools very early. I would say at the time we didn't know it was called machine learning. So I was using clustering algorithms and so on. So I was exposed somehow to machine learning without really knowing that this is called machine learning. And from one algorithm to another, I discovered those magic libraries that were published in Python that could do the job automatically without the hustle of coding things line by line.
All the way from scratch.
Exactly, yes, yeah. So this is how I started, and then came neural networks and computer vision and large language models and so on. So it was hard to quit back to normal coding, I would say. Yeah.
No, I mean, it's a I definitely sort of from an academic perspective also came from a background where the route towards data science was way more through more general, sort of seeing them in a more general sense of algorithmic work and vector space sort of thinking, and not through the lens that in the world of technology we do, which is more around that application, and is more the way where you find the useful thing that you probably want to solve with it. And so it's interesting that it was similar for you, and I don't blame you for not wanting to quit. So large language models, I said at the start, they really are the buzzy, huge sort of topic at the moment in data science and tech more broadly. They're seeming to be incredibly disruptive right now with GitHub Copilot, with ChatGPT, and really there seems to be a potential that they're going to change lots of the way we work in lots of different career paths at the moment. You've done some work with them. You're about to teach us a lot more about how we can use them. But with all this change coming so quickly, what's the direction things are heading in? Any clue on what's coming next with large language models?
That's a very nice question, because I think it's an open question. The limits are not there. I mean, so far language models are basically used as chatting models, or chatting agents, coding agents as well. So it's limited to the context of what you get back from a screen perspective. Like you put your input and then you get back something that's on your screen. And what I'm curious about, first of all, is the quality that these models are going to improve within the next couple of years. But it's also, what if we gave a little bit of hardware control to some of these models? Like, could the model be able to automate, for example, your light control in your house or in your infrastructure? Like, just giving a bit more control to these models when we know that the quality is enough to do this. This is it's something I'm curious about, because we've seen it with Alexa, with Google, and with the previous hardware. But I'm really curious how those large language models would be extending these applications.
No, that's a really, I guess, I hadn't thought the answer was going to go in that direction. That's really interesting, and I guess it just goes to show applications are potentially wide ranging for this stuff, and actually that leads kind of nicely into the other thing that's been on my mind, which is, as someone who's a bit of a novice to large language models, and that's why I'm excited to talk to you today. What is the sort of use case? Say you've got a problem in front of you. What's the trigger, or when would you turn to trying to utilize and trying to fine-tune a large language model in the way we've described today, versus some of that traditional natural language processing type algorithms and work?
Practically, you can basically use these models anywhere from chat agents, replying to customers, automating all these pipelines, segregating and clustering types of messages that you are getting through an infrastructure to forward these messages, for example, to relevant departments or relevant persons that would be able to help users. I think the applications are unlimited. It's up to the use case, but the quality that these models have reached today are making these opportunities wider now. These models started a long time ago, I would say, like 5 years ago, but we never heard about these kind of applications because the quality of the results were limited somehow. So now it's regarding the applications, it could be anything and everything.
And so I guess it comes down to that quality is high now, and that generative component you're getting out of it just blasts open the boundaries on perhaps how you might be able to apply.
Yes, exactly, because previously we wouldn't be able to do sentiment analysis using language models. We needed to go through the classic Spacey and other libraries of language processing. So now it's possible to do it through language models. You don't have to, again, code line by line what you want the model to do and so on. So the language model can handle this automatically, and this is very powerful. I don't want to spoil the first slide, but the first slide will show 3 different examples on different tasks that we used to use different Python libraries to do these, and now they can be handled automatically using ChatGPT or any large language model.
So there's definitely a degree of now the qualities there again that overlap in approaches you can take and ways of doing it in a lower code way. That makes sense. So you mentioned maybe I'm starting to probe too far and get into the slides. I think this is the perfect time to actually move on to the presentation. So big thank you for entertaining my questions, Ziad. That was really interesting, and I'll hand over to you to take us through the presentation.
Thank you, Max. Okay, so I will start with the first slide. Showing 3 different examples using ChatGPT beyond just chatting. So obviously we can ask a question to a language model or assign a task, and we would get an answer back. But we can also try to ask the model to apply sentiment analysis on a sentence. So this is the first sentence. It's an example. I asked ChatGPT to provide me what is the sentiment expressed in this sentence on a scale from 0 to 1, and the result was very accurate. I would say it's providing zero 0.9 as a positive sentiment, and it's also providing a kind of an opinion or an evaluation of the sentiment expressed in the sentence. Another example is the named entity recognition. So I also put this query for ChatGPT: apply NER analysis on this sentence. PA Consulting is organizing the session, and Max is a great host. And here's the named entity recognition analysis for the given sentence. So ChatGPT recognized that PA Consulting is an organization, Max is a person, and so this is just one example. We could try these on larger paragraphs and larger texts. I also tried zero-shot classification. I provided another sentence as an example and provided some labels, candidate labels, and I asked ChatGPT to assign a score of this for these labels, taking into account the input sentence. And we can see that science got a score 0.9, which is the highest score because the sentence was more related to a science topic. So these are three examples showing the potential of language models and how we can use these beyond just chatting bots.
Out of interest, because those were really nice examples, and I think that speaks to just the thing we were discussing a minute ago against some of those traditional things you might want to do with NLP and how a large language model can help you do that. Quick question, how long did it take you? Did it take much refinement in terms of how you asked those prompts to get the things you wanted, or was it pretty straightforward and it understood what you were asking pretty immediately?
That's a good question because it depends on the model you are using. Now, I tried these examples on ChatGPT where no fine-tuning was needed. So it's straightforward. You can put the paragraph there, your text, and ask ChatGPT to apply the analysis you want to achieve. However, with different models, if we're downloading models from Hugging Face repo or any other models, we might need to fine-tune these, and not all the models are capable of applying these tasks. No, so it's specific to some models.
It's like traditional data science has a degree of testing the waters and seeing where you stand and what's coming out, I'd imagine.
Yes, yeah, exactly. It's time consuming to test the different models and check what are the capabilities of each of these models. So that might be something that's tedious at first, but once you found the model that's good for your task, it goes fast from there. Yeah. So where we can find language models, there's a community called Hugging Face sharing repos. Currently, I counted 75,000 language models on Hugging Face, and the number is increasing with the number of AI users and developers every day. I think this is a rough number, but I think it's growing in thousands because the repo is available freely for all the users. We can download any model and fine-tune the model, apply some small modifications, and then repush to the repo for other users and for the public. And this is why it's kind of I would say, democratizing language models and giving access to any AI user to acquire these models. So we talk about language models and the number of parameters. I just took this curve from the Hugging Face documentation showing that we started with a very low number of parameters in a model, and this model increased exponentially. And today we're talking about a double exponential increase in size. We can see GPT-1 from OpenAI in 2018. It wasn't a very large model compared to today's models. For example, it was, I think, 110 millions, or I can see it's a bit small, but anyway, it's around 110 millions. And then we got GPT-2, which was a bit larger, and 1.5 billion parameters. GPT-3, 175 billion parameters. This is the ChatGPT open to the public today, 3.5, and GPT-4, 170 trillion parameters. So there are different models now that were out since the time I prepared this presentation. Things are becoming obsolete very quickly. And There's the Falcon model, 40 billion parameters, that was trained on clean data. The effort was to provide, let's say, better quality data and to clean the model on this data and then get a better result with a smaller model. We don't have to exceed a certain threshold of number of parameters. So 40 billion parameters could, I would say, compete with 175 billion parameters, provided you train the model on clean data.
So that quality is not all coming down to parameters, meaning more intelligence. There is the inputs. There is obviously the inputs are important. It makes sense. It's easier to sort of, when thinking about a new thing, to forget that we're always trying to clean data and make sure we have the most appropriate data for the model at hand.
Yeah, I think in data science that's going to be the most time-consuming task and the most important task, cleaning the data. Yeah. So later in the presentation, I will be talking about the LLaMa models provided by Meta from Facebook, and they provided 4 different models of 4 different sizes, 7 billion parameters, up to 65 billion parameters. And this is another curve that I found on Hugging Face on a nice article. We're talking about a new Moore's law, which is replaced today by Nevin's law, the vice president of engineering at Google. And it's a curve that shows the increase of the size of these language models with time. And it's roughly, we could say that the size has been increasing 10 times every year for the last few years. So we can expect something, a quick development in the coming 3 or 4 years, depending on the hardware as well, because the larger the model, we might need larger hardware.
So in direct comparison to thinking about Moore's law, why is it so fast? Why is this increase in scale happening quite at that rate? Is it a hardware thing or a cloud sort of compute thing, or is it just the amount of people pushing on it right now?
I think it's a bit of everything.
Yeah.
It also reminds me that why did we call machine learning very recently, a few years ago? The math was known since the 60s, but neural networks were there since also the 60s. So we didn't get access to these until recently because of the hardware availability. And I think the hardware it plays a big role in how much we can develop these language models, but also the developments of open source communities such as Hugging Face, where everyone can also acquire these models. And the hardware is also available on the cloud. We could rent it for relatively cheap. So we can rent GPUs per hour and deploy these models and start using them from anywhere in the world.
No, absolutely. Yeah. That makes sense.
So for fine-tuning a model and enhancing the performance of a model, there are 2 approaches to customize a language model. We're going to discuss these today. The first one is to fine-tune a pre-trained language model. The story of a model is the following. So when we are developing a language model, first we have the model, the raw untrained without any data. Then we apply pre-training on a large corpus of data. And this operation is the most costly and from compute time-wise and cost-wise and the data-wise, because you need a large corpus of data. So you need to clean the data, you need to have, this is not individual scale operation, it's organization scale operation. Then what we download from Hugging Face is the pre-trained model. This is the GPT-2, 3, the LLaMa model, or any other models. These are pre-trained models. We can use these as they are, out of the box. Or if we have a small set of data that we want to ingest in the model, somehow the model could pick up the style of a chatting or a writing style, or we can apply a fine-tuning operation. For this, we can do it on few GPUs. So it can be, with decent hardware, we can do it on individual scale. And then we get our fine-tuned model that we can use. So that's the fine-tuning path. There's a different path, which is the prompt prompt enhancement. It works with bulk data using pre-trained or fine-tuned language models, which means we can use either the pre-trained model to enhance the prompt, or a fine-tuned model as well to enhance the prompt. And in this case, we would be using both approaches at the same time. So we get a fine-tuned model to which we enhance the prompt before getting the answer. We're going to talk about these in detail later on.
Nice. No, it's good to know that there's two different approaches there.
So I'll start by checking the architecture. We have to talk about transformers, which is the architecture behind these language models. It does all the magic. We will see why do we need transformers, what is special about this architecture, and how we can train these for specific tasks. This is the overall architecture as published on Hugging Face by Google as well. They published a paper entitled "Attention is All You Need," and we're going to talk about attention mechanisms today, which are a big part of this architecture. Most importantly, we can see that we have two parts in this architecture: the left part and the right part. The left part is called the encoders, and these encoders are responsible for processing input text sequences and capturing the context and the meaning of sentences and sequences and words and so on. And some examples of where encoders could be useful are sentence classification, sentiment analysis, named entity recognitions, word classification, and extracting question answering and so on. So anything that's related to the context of a sequence. And some of the example models are the BERT family that are also published on the Hugging Face community. The right part differs a bit. It's the decoders, and these are mostly responsible for generating sequences. So if we give 3 or 4 words, a sequence of 4 words, the decoders are able to generate the most probable future words, or the words that could follow these the sequence of words. And these are the models that are responsible for chatting and generating new sentences, answering questions, and so on, such as ChatGPT or the whole GPT models and others. We also have some models that have an encoder and a decoder at the same time. These are called sequence to sequence, and these are mostly used for translation from one language to another, because we could capture a context from one language and try to generate the same sentence in a different language within the same context somehow.
That's a really fascinating use case, because the idea of capturing context, translating context, and then sort of being able to generate something that means the same thing, I think speaks to the detail in what we mean by context here, and how sort of powerful they are.
Yes, actually the coming slides we will talk about attention mechanisms, and we will be focusing on how the context is captured in numbers in these sequences.
Makes sense.
So now I'll be talking about attention mechanisms, but before that, we will see how the classic way of generating sequences used to happen, or at least the first time we tried to do it in AI. I'll take this example. So it's the apple is tasty. For example, this is just a sentence. The word vectors of these words are going through a neural network encoder that would generate a hidden state. Then the second word in the sequence we will also take the word vector embeddings. We will inject these into a neural network encoder, but we will also take into account the previous hidden state of the previous word. So now the new hidden state, H1, contains information of the last 2 words, or the first 2 words. And then we inject this information, the H1 hidden state, into a new neural encoder with a new word, and we get a new hidden state, H2, with the information of the previous 3 words, and so on. So to apply translation or any kind of information, we inject the for the decoder the last hidden state. So the decoder in this case has access only to the last hidden state, and this architecture is serialized, so it causes a large number of transformations before reaching the decoder. And anyway, the decoder has access only to the last hidden state, so there's no importance to any of these words. They are all somehow uniform. Their importance is uniform in the representation of the last hidden state. This architecture poses two, I would say, in brief, two main issues. The first one, it's computationally more expensive because it's serialized. We can't parallelize this. And the second one is for long sequences and long paragraphs and sentences, some of the words that were mentioned at the beginning of the sequence might be drowned down in the noise or in the numbers of the other words in the sequence.
It goes through hidden state to hidden state. It's almost too diluted, I'd imagine, for those things that were way earlier in the sequence.
Exactly. So if you are interested in translating now the first word, you wouldn't get much of the first word information in the last hidden state. And this is where the idea of attention mechanisms came in. It's basically trying to give access to the decoder to any of the hidden states directly, instead of just considering the last hidden state. And the best way to explain this is to take this example. For example, this red wristband. The word band could mean music band or wristband. But if we take the sentence, we would know what the context is, and then we would understand what is the true meaning of this word. So let's consider we have these vectors of embeddings of these words. The first thing we're going to do is to imagine that we have some magical weights that would include the context.
Yes.
So if we could multiply these vectors by something that is related to this sentence, because the context is within the sentence, so we need to multiply these vectors by those weights that are coming from the sentence itself to apply this context. The way we are doing this first is by using a dot product. So we will multiply, for example, the word bend is causing confusion here. I'll take it as an example. I'm taking the V4, so these are the embeddings or vectors of the word bend, and I'm applying a dot product between V4 and all the other words. So V4 with V1, V4 with V2, and V4 with itself, V4. I will get a score that we can normalize, and the normalized scores, we can call these weights now because they are normalized to 1. And then we apply another dot product. We multiply the weights basically by the vectors again, and we apply a sum, and we get improved embeddings. So this will be, A4 will be my new improved embedding for the word bend. The reason this works, why does it work, why this includes the context, is because when I'm applying a dot product between two vectors, if these vectors are pointing towards the same direction in the language, meaning previously these two words might have been mentioned frequently together in the text corpus where we got those vectors from, and therefore they share similar or close embedding vectors. So the dot product between two similar vectors is going to be very high. It's a high weight.
Absolutely.
While the product between two vectors pointing into two different directions is going to be very low. So the A4, the new improved embedding for the vector V4 or for the word bend, is going mostly to be influenced by those words that are very close or share a very close embeddings or close vectors to the word bend.
That makes sense.
So, and this is why we know band is related to wrist rather than this or red or anything else.
And so if it had also said this red rock band, they would have also had a strong, similar sort of sort of appropriate embedding, and that would have been the thing that would have helped us know, well, it's not a wristband, but because they're mentioned together and they've got that similar dot product or vector direction, which results in a high dot product.
Yes,
It all comes,
exactly.
It's funny.
Yeah.
I mean, we were laughing at the start about approaching machine learning from that algorithmic, from that vector space perspective, and it's so interesting to me how things like this attention mechanism, which by all intents and purposes seems very effective and clever, is still built on quite basic principles, really.
Yes.
Once you've got those word embeddings, and once you're working with them, it's, well, what is the sensible way of, of utilising that in this relatively known sort of mathematical world and field?
Yeah, that's. I mean, it's amazing that, as you said, it goes back to a dot product.
Yes, yeah.
That's it. Actually.
Blows my mind.
So, so in brief, we have those embeddings. Then we have the improved embeddings, because this operation is repeated for any word in the sentence. And we can notice three things. First of all, the word's proximity and order in the sequence have no influence. And the second point is that the approach is applicable to different sequence sizes, so it's shape independent. We can apply it to long paragraphs or to short sentences. And the third point, which is very important, the improved embeddings, A1 to A4 here, they are good, but we have no control over. So if we are not happy with the results, we can't fine-tune anything.
It's just a fixed process, isn't
yes.
it? And it's all programmatic and algorithmic. We're having no control over weights or parameters.
Not yet. Not yet. Well, in machine learning, we're always used to fitting a model before using it.
Yes.
And it's going to be the same here. That's the purpose of the attention mechanism. The way we will do this, first of all, we're going to give different names, queries, keys, and values for the same embedding vectors. So these are not different. It's simply where we are using these vectors. This is why we have different names. And we will introduce some matrices, squared matrices of weights. We will multiply these queries, keys, and values by these matrices. And we will be fine-tuning the weights of these matrices. So we're simply including some parameters we can play on, that we can change, so we can change the outcome also of the model.
Good.
So one important, this can be redrawn, the architecture can be redrawn in this way. So we multiply these, maybe I should go back to the previous slide showing that we're multiplying these, and it's exactly the same operation. So we get the weights, we apply the multiplication, and then we do the sum, and we get our improved embeddings. Only this time, we can redraw this architecture this way. So we have these matrices where we can include our weights.
Yeah.
We multiply these by the different vectors, we get the weights, and we get our contextualized embeddings or improved embeddings. And the whole thing is called self-attention block, because we're getting more attention on some words where the embeddings are causing confusion. So we give this more attention, and we can get the context of the sentence to get the full meaning of the word. So one thing to know, I will not go through the details, is the way we are changing these weights is by propagating the information back from a result, from a labeled result, and using gradient descent. Yeah. So this is a full topic on its own. It's basically doing differentiation between two different values, checking the slope.
Yeah.
And this is what's called gradient descent or gradient ascent in mathematics, to optimize the results to a labeled outcome, to a labeled output. In order to give more flexibility and to be able to capture more contexts, instead of just using one sentence, if you have a lot of different contexts in a paragraph, we can make the system more powerful by including more than one matrix of weights to be fitted. So instead of using one block, one key matrix, and one queries and one values matrix, we're going to use different matrices. And this is why we call this a multi-head attention mechanism. It's because we're using different heads for the block. All of this is going to propagate throughout the network, throughout our computation, and we'll get multiple sets of improved and contextualized embeddings. And these can be concatenated into a dense layer to be used later on.
Yeah.
One more important thing is that these are very flexible. So any multi-head attention mechanism or attention block can be plugged into another one in series. So we can fit multiple attention blocks together in order to fit. If we have a large corpus, I would assume that we would need more than one attention block to fit to some millions words. Yeah,
it makes sense. And it's that come up with something simple, spread it out with that ability to fine-tune and propagate and have process for sort of fine-tuning effectively, and then start spreading out and multiplying out and making sure the level of detail can be increased as a result. It's a nice progression through this.
So transfer learning, the fine-tuning part happens right here. So this is why we have, in this architecture, we have the multi-head attention, and we can see that we have 3 arrows going in the attention block. This is because we have the queries, values, and the keys, those 3 matrices we talked about. And some details about this architecture, we can see that we have an X here, for example, and one here that's hidden by the arrow. It's because we don't have one block in each model. We can have different blocks that are connected together, but it's basically the same architecture. We also have the positional encoding. It's mainly because if we need to take into account the position of a word in a sequence, we need to apply some positional encoding or labeling, because the multi-head attention blocks will not do this. So Hugging Face provided a large set of libraries. There's a paper called LoRa, Low-Rank Adaptation of Large Language Models, demonstrated that fine-tuning can be performed by freezing the pre-trained weights. So we're not touching any of the bulk of the weights of a pre-trained model, which is good, because we're only fine-tuning, I would say, less than 1% of the parameters when we are fine-tuning a model. And this is why it's possible to do on a consumer level GPU.
Absolutely. We don't want to have to do it at that scale, because, well, then we might as well be starting from the start again.
Yeah, exactly. They open the door somehow for users to be able to fine-tune the model, playing only on a small set of parameters. And it's all happening here in this multi-head attention block, and on these precise matrices that we precisely on the matrices that we just described in the previous slides. From the hardware size, from the hardware requirements perspective, we need to know that any model would require at least, let's say, 7 gigabytes of VRAM. That's GPU RAM. I'm talking about the LLaMa models, the smallest one, 7 billion parameters. I would say any useful model, because below this, models do not perform impressively well. And we could go up to 135 gigabytes of VRAM for the largest model, which is 65 billion. It's still smaller than most of the models, the large models, but it's also accessible for users. We can also quantize the weights of the model, decreasing the precision of these weights from float to integer, from 8 bits and so on. So it's basically a library that does this. I've seen users quantizing down to 4 bits precision. And I don't know about the quality. There's always a trade-off between the precision of the model and the size of the model and so on, and the quality of the results that we're getting. I tried the 8-bit quantization, and I managed to run the LLaMa 7 billion parameters on 7 gigabytes VRAM, and the 13 billion ones on 14 gigabytes VRAM. The rest, I didn't have time to do it, because anyway, it's hardware consuming and time consuming. Loading the model itself takes a lot of time also.
I mean, just looking at that scale, it would, and it feels like that those different ways of trying to optimize for resource needed, it's interesting, and I'd imagine there's not tons of research, there's not tons of laid out experience of when you might want to quantize a higher parameter model versus when you might want to use a lower parameter model, and what those use cases are. But I'd imagine at some point that will start to become more known.
It's kind of frustrating operation. It's a trial and error, and it's very time consuming, and you never know what you will get as an outcome until you try it. I mean, there's a large community, and you might find thousands of models with different quantization, different fine-tuning operations, and so on. So when you download the model, it's time-consuming, hardware consuming, and then if you want to quantize on top of what you got, on top of the fine-tuning and so on, better be careful and take notes what you did, because at some point it becomes it's a full-time task, I would say. It's a full-time task before taking a decision that this is the optimal setup that we would like to use.
Yeah, makes sense.
I will talk a bit about the LLaMa derivatives, because since LLaMa was released, we can see here the set of data. I will not go through the details. We can see Common Crawl, C4 GitHub, and Wikipedia. So this is the data source that LLaMa was trained on. But LLaMa is a decoder model, so it's a sentence completion model. It's not a chatting model. We have to fine-tune it to be able to chat.
Yep.
And this is what different research groups did. The Stanford Alpaca group fine-tuned on, I think, 52,000 instructions. And by instructions, I mean one typical question and one typical answer. So these were generated in a very smart way. 175 were human written, 175 questions, answers were human written, and the rest were generated using ChatGPT. They asked ChatGPT to generate something similar to what they provided as seeds or human written seeds. They got 52,000 instructions. They went through cleaning and quality control of these instructions. But it was a pioneer study that opened the door for other groups to do the same with different sets of data.
I guess that's the question, isn't it? As much as anything else, how can you creatively and efficiently start to produce those right sort of inputs at that scale is like a difficult question that requires ideas. I'd imagine.
Yes, it's hard to get data. Data was always the problem in machine learning and neural networks. And at this point, we're getting a bit creative in the ways you generate data, synthetic data somehow, but you need it to be as close to reality as possible. Yeah. And so then other groups like the Koala used the 13 billion parameters. I'll not go through the details. Both of these groups used ShareGPT instructions. ShareGPT is a website where users of ChatGPT are sharing their discussions with ChatGPT. So the data is out there, the information is there. Some groups are taking this information and using it to fine-tune different models to perform just like ChatGPT.
That's really interesting.
And the interesting part about Vicuña is the way they evaluated their results. They divided they asked GPT-4 to provide questions that are usually hard to answer by language models. Yeah. So usually where basic language models would fail. And then they asked these questions to different models that we're going to see. To LLaMa, 13 billion, Alpaca, Vicuña, Bard, and ChatGPT. And they asked GPT-4 to evaluate these answers, the answers provided by the different models, based on the quality, based on helpfulness, relevance, accuracy, and detail. And we can see the results that the least performant, which we would expect it to be, is LLaMa, because it's not a chatbot. It's a sentence completion model. But then Alpaca performed a bit better. Vicuña 92%. And it's compared to ChatGPT, which is the reference because it's GPT-4 that's doing the comparison. So we can see that with a very small model. I mean, 13 billion parameters compared to GPT-4 or GPT 175 billion parameters. Yeah. It's really there's a factor 10 between the size, but we get 92% score, which is not bad with such a small model.
No, not at all. And when you're thinking of trade-offs and thinking of how you will access these models over time as well, which you will need to pay for and which you can get your hands on and things like that. It's interesting how much is going on in the open source community and how, I guess, the ability to impersonate almost existing models is something people have looked into. It's fascinating.
Oh, yes. I mean, this is something I'm very curious to see regarding your first question, like what would we expect in a couple of years, coming years? I would expect a very small model performing as good as a very large model.
And that,
at least I'm hoping for it.
Yes, it's an exciting or interesting thought in what that then means application-wise, or what doors that opens.
Yeah, maybe a future large language model running on your phone.
We can dream.
So this is the fine-tuning path. Now I will be talking a bit about the prompt enhancement. And we recently saw a lot of courses online and a lot of topics discussing the prompt engineering part of language models, because it's very important to know how to query whatever, how to make the model provide you a good feedback or a good answer, good quality answer. And this also depends a lot on the prompt you are or the input towards the model. So the user has to be aware of what the model is capable of and the limitations of the model.
Naturally, yeah.
But there's a way to enhance the prompt. If you have data, any information like PDF, folders of texts, and so on, there's a way to segregate or slice these texts into smaller chunks of texts that would fit into the prompt limit of your model, and then try to store the vectors or the embeddings of these slices of text into a vector store. And whenever the user asks a question, we would check which is the chunk of text or the slice of text that's the most similar or relevant to this question. We would concatenate this piece of text to the question, and we pass the whole thing as a prompt to the language model. So this way, the language model has the question, the query of the user, but it also has a piece of text from your text database that is relevant to the question of the user.
So this is sort of like in some traditional like computing style sort of fields instead, where there is a layer in between what you are inputting and then what is effectively being passed to the engine under the hood. That is almost like preparing it to be ingested and used sort of most effectively.
Yes, exactly. So it's automating the prompt engineering in the background somehow. This is also something I find it very important and very nice to work with, because I've done some prompt engineering in the background. I've had the chance to do this at PA, and it really plays a lot on the outcome and on the results you get from the model. There's a library called LangChain to do this, and there are 4 different ways to pass the prompt to the model. Either we use the stuffing method, so we take any slice of text that is relevant to the question, we pass it within the prompt at once. That's not the best method, but it works if you have a small prompt or a small chunk of text, because also the prompting the language model is limited by the number of tokens or the number of words you could input to the model. So you can't chat with a model providing a PDF book, for example, or and so on. So it's limited. LLaMa, for example, is limited to 2,000 tokens. Okay. I think it's also something very similar to ChatGPT. I think it's something around 2,000 tokens as well. So there are different ways to deal with this. If you have a larger chunks, slices of text that you would like to put into the prompt, we can use the MapReduce method. and any task, for example, I took here a summarization task. We can apply this task to the first chunk, to the second chunk, and so on. So these are summarized. We get smaller sentences, and then we apply all of these, we concatenate these summaries, and we put these into the prompt for the language model, and we get our result, taking into account the whole bulk of slices of text we would like to include in the prompt. So it has some disadvantages. There's an advantage that you can try to squeeze in as much information as you want, but at the same time you have potential loss of information during this combination process due to the nature of the integration process.
That makes sense. If you chop up a sentence, do something to it, and then stick it back together, you might have lost some of those contextual bits, or you don't have necessarily control over what those slices are.
Yes, and you know, applying summarization after summarization, you might start losing this information at some point.
Abstraction,
yes.
isn't it?
Yeah. Another way of doing this is to apply the task to the first chunk, just passing the first chunk and the query to the language model, then taking the result and asking the model to refine this answer by passing the chunk 2 regarding chunk 2 or the second slice of text, and then taking whatever we get as a result and passing it again to the language model with a new slice of text and asking the language model to further refine the answer. So this works in serial mode. As you can see, we can't parallelize this. And if compared to the first method, which is the stuff method, where we call the model once, these two methods, the MapReduce, are calling the language model more than one time. Absolutely. And might incur extra cost, more time, more computing time, more processing time, and more cost basically. Yeah.
And so again, it comes back to that role as the data scientist to understand what benefit you're getting out of it, and what's the balance that feels right to make sure performance is at a certain level against that cost.
Yes, there's no way to guess in advance, I think, what's the perfect method for your use case. I think maybe with time, using those methods over and over, some AI people or data scientists might get the experience of trying to guess in advance which one would be the optimal way to use. Which is the optimal method to be used.
But for now, we're just at that stage of adding tools to the tool belt.
Yes, it's very experimental at this point, and trial and error. And one thing in this refined method is that the order of the documents of the slices might also influence the output. So if we shuffle the chunks of text or the slices, in this case, we might get different answers. But usually, the way we deal with it is that we rank these by a similarity, and the first slice of text that we will pass to the language model is the most similar or the most relevant to the question of the user.
That makes sense. So there's just these sort of slightly added layers to sort of build up that mechanism.
One last method using LangChain is the map pre-rank. So we will pass the different slices of text to the language model, and we will apply the task. So if it's a summarization, for example, or any NER or any kind of task, we will ask the model to apply this task, but also to provide a score of certainty. And we will only select the answer with the highest score, and we just discard the other answers. So it does require asking the model or querying multiple times the model to do the task for the different slices of text, but it also provides a very short answer regarding it's actually leaving the decision to the model to decide like which is the most relevant answer that you will be getting.
Yeah.
And finally, I just wanted to highlight the Hugging Face community. If you need to download your models, you can fine-tune these on on a GPU. You need a decent GPU to do this. And using LangChain also to enhance or to chat with your documents. This is, I've seen a lot of articles online and bloggers describing this as if you would be able to chat with your documents. And it's true, because actually you're chatting, taking into account whatever data you are ingesting into the model. Yeah, so these are the two models I wanted to talk about today. And I don't want to forget to thank the whole team who's been supporting this work. Thank you, Max, and Chris. Thank you so much. I know we don't see you on the camera, but thank you so much for your time.
Fantastic. Well, big thank you, Ziad, for taking us through all of that. And I think in a minute we're going to move on to a code walkthrough and demo that's sort of pre-recorded, where we'll be hearing more of your voice as you actually step through some of the code behind the scenes and how some of this works in practice. But before that, I want to say, big thank you. I know what I'm going to be doing after this call. I'm going to be getting on my laptop and browsing Hugging Face, I think, to take a look at how many thousands we're at now and maybe try downloading something and playing around. But that will be all from us in sort of live as part of this stream before we hand over to the demo. Thank you for tuning in. And if you'd like to see more of what we're doing here as part of the Real Data Science meetups, I'd really recommend join our meetup network or subscribe to the YouTube channel to see what's coming up next. Again, we'll have another one in the next month or two for sure, and I'm looking forward to it. So that's all from us. We'll play the walkthrough now, but big thank you. Thanks, Ziad.
Thank you, Max. Thank you.
So for the fine-tuning, I'm using a Jupyter notebook for this demo. First, we are importing packages, so datasets, transformers, and the LLaMa model and its tokenizer, and the PEFT parameter efficient fine-tuning from Hugging Face to be able to fine-tune the model. Then we can load the model and its tokenizer. So I chose the LLaMa 7 billion, which is the smallest model. There are different models on Hugging Face that we can load and fine-tune, and they are already fine-tuned for different tasks and different versions from this same model. Load in 8-bit true, so we can try and save some memory. The device map is set to automatic, so in case you have multiple GPUs, this is going to load on multiple GPUs for better performance. And again, I'm passing the model as an argument to this function, prepare model for int8 training, so we can fine-tune the model or train the model in lower precision. Then we're using the low rank adaptation for large language models, LoRa module, dropout parameters, and the alpha and R parameters. So I didn't really change these parameters. I'm using them as by the sources I found on Hugging Face and in documentation. But the most important we can see are these modules here, the target modules. And these are the queries and the values layers that we're going to fine tune in our attention modules or multi-head attention layers. And if you want to fine tune also the values matrices, it's also possible. But basically we want to start with only the queries and the values and change things gradually from there. So I didn't try, because this is time consuming, I didn't try all the possible combinations, and there are different options also offered by the LoRa package. But this is a good start if you want to start fine-tuning your model for the first time. And also the fact that the names are Q and V and K, just like queries, values, and keys, is a kind of confirmation that the fine-tuning is happening in attention layers. Then I will have to define a new function called generate prompt that takes a data point. And our data points, if we take a look at the sample data, this is mock data, by the way. I just created these for the sake of this demo, and this is how it looks like. So we are providing a JSON file with different points, instruction points. So a point for us, a data point, is an instruction and its output or its answer. And this is where we have a typical question, and this is the label or the answer to the question. This is why this part of the fine-tuning is supervised learning, because it requires the instruction and the label or the answer. For this example, I only included 10 data points because this way it's faster and shorter for the demo to run. If you have a larger data file, your training is going to require more time. So I'm building my prompt this way. I'm going to transform those data points from my JSON file using this prompt. So this is an instruction in the form of a query or a question, provide an answer. If you don't know the answer, just say that you don't know. Don't try to make up an inaccurate answer. So I'm trying to reason with the model a bit here. There are different ways of doing this. I don't think this is the best way. You might want to experiment on this part or maybe do some more research because this is model specific. It's not the same sentence or the same prompt that we're going to use for different models. If you are loading a different model other than the LLaMa model, for example, you would want to modify your prompt in a way that fits the model and provides you with the best results. And after the prompt, we're adding the instruction 2 points. And notice the separators, the 3 dashes here. These are added on purpose because of the documentation of the LLaMa model and the Stanford Alpaca fine-tuning work. They also use these 3 dashes. Apparently, the LLaMa model requires these because this is the way it was trained. And it uses these characters as separators. So we're inserting the instruction here and then the response. I've seen different studies like the Stanford Alpaca. They put instruction, prompt, and response. So the query is basically, or the data point is made of 3 different keys. So you have the instruction, the prompt, and then the output. We are using the simplest form because we have a simple form of data. We have an instruction and then typically an answer to it. And this is the part where we load the data file and we tokenize and we generate our prompts. We apply padding as well and truncation, 512 tokens for now. And then this is where all the magic happens. This is where we're going to use the trainer function from transformers to fine-tune our model. The trainer function is a wrapper that is provided by the Hugging Face and it does the fine-tuning automatically. So it takes the model, the training set, tokenized training set, a set of arguments, and a data collator parameter. The arguments are defined here, and the most important ones right here. So we have a micro batch size, which is equal to 8. So in case we are training on multiple devices, multiple GPUs, this is the batch size that's going on one GPU or per GPU. Then we have the total batch size, 128. And the gradient accumulation steps is obtained from the batch size and the micro batch size. In this demo, I run this demo on one GPU, so it doesn't matter much. If you're working on one GPU, you don't have to worry much about these parameters because basically it's going to be the batch size that matters. And then we have the number of epochs and the learning rate. The number of epochs, it's very important for people working on neural networks. We're used to putting a large number of epochs in numerical training. But in the case of language models here, the original paper fine-tuning the LLaMa model uses 3, and some users were using 2 epochs in order to avoid overfitting. So typically more epochs will lead to overfitting, which might be needed in some cases. I don't know, if you don't have a lot of data and you want your model to stick with the data and the style that you have provided, you might want to overfit your model. But again, this is all experimental, so we can start with 3 or 4 epochs and change things. So we can start with 3 to 4 epochs, I would say, and I just ran 10 epochs on the sample data I'm using for this demo because I only have 10 points and I needed to make the training or the fine-tuning time a bit longer. It took a few seconds just to train over 10 points. For the learning rate, I used what is used by LLaMa and Stanford Alpaca as well. So we don't have much room to change these because the training takes a lot of time. So if you want to experiment on all these parameters and check the outcome, you're going to spend a lot of time trying and testing your model. And this is it. Once this part is done, we can simply launch the training operation. And we can see we have 10 epochs here. The training loss, it didn't decrease much. We don't have enough data. We don't have enough epochs. But typically, if you have around 40,000 or I would say 10,000 points, you should see straight decrease in the training loss after 2 or 3 epochs. Then we can save our model for later use. And now we can start using whatever we have fine-tuned. So I'm using the same prompt. We need exactly the same prompt we have been using for the fine-tuning. And I'm tokenizing the instruction with the prompt. So now I'm asking the model, tell me about PA Consulting and their expertise in cloud computing. And I'm going to pass this to the function called generate, along with other parameters such as the temperature, the top P, and the repetition penalty. These are basically, if you're not familiar with these parameters, it's basically how much freedom you want to give to the model to get creative. If we decrease the temperature, it means that the model is going to stick with the highest probability sequences as answers for our question. And if we increase the temperature to, let's say, 0.9, the model might get a bit creative. So again, we have maximum new tokens limit. So this is our first question and answer. We also use the tokenizer to decode whatever the model has generated. So tell me about PA Consulting and their expertise, etc. The response is, we are experts at providing consultancy services for companies who want to move into cloud, etc. So we didn't provide all of this in the data points. I don't believe we have all this description. This is all the language models making. The instructions and the outputs, they all concern 3 different persons. These are my colleagues. And I didn't provide anything general about PA Consulting. So if we take a look again at the answer here, it's somehow refurbished to fit with the question that we have just provided. Now you may notice that we have another question. Again, what do I need to consider before moving my company's data, etc., onto the cloud? So we didn't ask this question. It's LLaMa, sequence generation model. So it's going to complete the sentences or the paragraphs with the most probable words that would fit with whatever we already have. So we provided the first question. It provided the answer, but then we didn't fill the 256 tokens yet. It's going to complete this paragraph with whatever next might be coming as a question. So what do I need to consider, etc. So this is also a question generated automatically by LLaMa because of what we have already asked in the first instruction. The answer is also provided by LLaMa, and then a question, and then I think it's truncated because we have a maximum new tokens of 256. So this is how we fine tune, but if you want to use LangChain with a tuned model, so we import LangChain libraries, and then we divide our text into chunks. I'm using exactly the same text, the sample data JSON file that we have used for the fine tuning. We're loading this, inserting some separators just to know when is one data point starting and when a data point stops. So a data point, again, is an instruction and its output. We're passing this into the character text splitter, and we're providing the separator characters, the chunk size, the overlap between chunk size, so we don't skip any sentences or truncate any sentences in the middle. We split the text into chunks. I'm just printing whatever we got here, so we can make sure that the split is done correctly, at least on a sample of our data. Then we define a new function called, let's say, respond. It takes the temperature, the maximum number of tokens, and the query. And we're defining a pipeline, a classic pipeline from Hugging Face. It's a text generation pipeline taking the model, the tokenizer, the maximum number of tokens, temperature, and the other parameters for the language model pipeline. We're putting all of it in a variable called LLM. So this is a Hugging Face pipeline so that LangChain understands what this is. We're using the embeddings of Hugging Face. So we don't have to be picky what type or which library of embeddings are we using or which model, because it's simply used for comparison of similarity between the different questions and the data chunks or the text chunks. Then we can define our vector base or vectors database, embeddings database. I'm using Facebook similarity search package. You can use Chroma. There are different alternatives. This one works well. So from text, I'm passing the text chunks and the embeddings. And then I'm defining a retriever variable. We're using the asRetriever function. and the search type is by similarity. We can also add a parameter here to say, like, we want to find the 2 or 3, for example, most similar text chunks. So this number can be limited. I left it by default. I'm not sure how many. I think it's 2 chunks of text by default, but we have control over this. And then we define a chain, a QA chain, question answering chain from LangChain. So from a chain type, we're passing the model. We're passing the chain type, it's stuff. So this was explained in the presentation. There are different ways to pass the information of the text chunks to the model. And the retriever is equal our variable, retriever that we have just defined. And return source documents equal true, meaning every time the language model is going to provide an answer, LangChain is also providing the source documents or chunk texts where it took the information from. And now we can start using the function. So defining the temperature, 0.5, maximum number of tokens, 200. These are the new tokens. And the query is, do you know anything about PA consulting? I'm calling the function with all these parameters, and this is the answer. So I have heard good things about them from my friends. They seem like, etc. So it's telling us a story. Another example, who are the top experts in cloud at PA Consulting? And Nunzio, Willem, and Clara are all considered top experts, etc. So this is clearly coming from the data we have just passed to LangChain and to the model. We just have to keep in mind that LLaMa, as is, the base model, is the smallest one. First of all, we're using the 7 billion parameters. So it's the smallest, it's the least performant, and it's not a question answering model. It's a text completion model and sentence completion model. So we can't expect a perfect result while asking questions. The best is to fine-tune this model, taking Vicuña, Koala, and Stanford Alpaca as models, and check how they did the fine-tuning, and fine-tune with data that looks like questions and their answers. And this way, the model will pick up the style of answers and the style of question answering and chatting. Then after the fine-tuning, we can use LangChain to provide the model with our custom data. And I think this is the best way to have optimized results and good answers. I hope this demo was helpful, and don't forget to follow for our next episodes of Real Data Science.